When you're working in a clinical lab, reliable is pretty much the most important word there is. But what does reliability really come down to when we're talking about test results? Well, it all starts with precision. It is the absolute bedrock of any trustworthy test. So today, let's dive in and really explore what precision is and what it takes to master it.
You know that feeling, right? You run the exact same sample a couple of times and you get slightly different numbers back. It's a classic situation in any lab. That little bit of scatter, that variability, that's exactly what we're going to tackle today. And look, it's not necessarily about being wrong, it's about understanding and quantifying the random noise that's just part of any measurement system.
So here's how we're going to break it all down. First, we'll nail down what precision actually is. Then we'll get into the numbers, how you measure it. After that, we'll look at the different levels of precision, figure out how to design a proper study, and finally, get to the big one, how to make that critical pass or fail decision.
All right, let's dive right in. Section 1. We have to start with the foundation. What are we really talking about when we use the word precision?
Okay, so what is precision, really? At its heart, it's all about consistency. It's that simple. It's your method's ability to give you the same answer over and over again when you're measuring the exact same thing. You can think of it as a direct measure of your system's random error, that little bit of unavoidable, unpredictable static in the process. And this is the classic way to think about it, and for good reason. Imagine you're throwing darts. Precision is all about the grouping. Are all your darts clustered tightly together? If so, you've got high precision. Accuracy, on the other hand, is about hitting the bullseye. The tricky part is, you can be super precise but not accurate at all. Imagine all your darts clustered tightly in the corner of the board. For a truly reliable test, you obviously need both. But you can't even begin to talk about accuracy if your precision is all over the place.
Okay, so we get it. Precision is about being consistent. But how do you put a number on that? How do you measure it? Well, to do that, we need to speak the language of variability.
And we've got two main tools in our statistical toolbox for this. First up is the standard deviation, or SD. Think of SD as giving you the raw spread of your data. It's an absolute number in the exact same units you're measuring. Then we have the coefficient of variation, or %CV. This one is all about perspective. It's a relative measure showing you how big that spread is compared to the average result. Now the formula itself looks super simple, right? You just take the standard deviation, divide by the mean, and multiply by 100 to get a percentage. But don't let that fool you. Its real power is in how it standardizes things, letting us compare apples to apples, especially when we're looking at results across a wide range of concentrations.
And this is the perfect example of why CV is such a game changer. Take a look. At a low concentration of 100, our SD is 4. At a higher concentration of 200, our SD has doubled to 8. Now, if you only looked at the SD, you might think your method is getting worse, that it's less precise at higher levels. But look at the %CV. It's 4.0% in both cases. This tells us the relative error is exactly the same, which makes CV an incredibly powerful tool for judging performance across the whole measuring range.
So here's where it gets a little more nuanced. It turns out precision isn't just one single concept. You've got to look at it from two different angles to really get the full story, the short-term view and the long-term view. On one side, you have repeatability, or what we call withinrunprecision. This is your best-case scenario, like a snapshot in a perfectly controlled moment. Same operator, same machine, same reagents, all in one go. But then you have within-laboratory precision. This is the marathon, not the sprint. This is what your test is really doing day in and day out, factoring in different operators, new reagent lots, and daily calibrations. This gives you a much more realistic picture of real-world performance. There's even a third level, reproducibility, that compares labs, but for today, we're focused on what's happening inside your four walls.
Okay, we've covered the what and the how. Now it's time to get our hands dirty. How do you actually design a study to measure all this stuff and get the numbers you need?
And it all starts with one simple but absolutely crucial question. What are you trying to do here? Are you a manufacturer, trying to establish the performance claims for a brand new test from scratch? Or are you a clinical lab and you just need to verify that the test works in your hands the way the manufacturer says it will? Your answer to that question will determine the entire blueprint for your study.
If you're the manufacturer, you're playing in the big leagues. You need the deep dive, and that means following the CLSI EP05 protocol. This is a serious study. We're talking a minimum of 20 days, often with multiple runs and replicates each day.
And it uses a really powerful statistical method called ANOVA. ANOVA is like a detective. It doesn't just give you a single number for imprecision. It tells you exactly where that imprecision is hiding. Is it within the run, between runs, or between days? That's vital info.
But hey, if you're a lab that's just bringing a new test online, you don't need to go that deep. You don't have to reinvent the wheel. You can use a verification protocol, like the one in CLSI EP15. This is designed to be much faster and more efficient. A common design is the 5x5. That's 5 replicates a day for just 5 days. The goal here is simple. Quickly confirm that you can get the same great performance that the manufacturer already proved.
Now, no matter which blueprint you're following, the deep dive or the quick check, remember this: your study is only as good as the samples you put into it. You've got to be strategic. Make sure you test at levels that actually matter to clinicians, especially right around those critical decision points. The material itself has to be stable and well mixed, and you want it to behave just like a real patient sample. Oh, and a huge practical tip: make sure you prepare enough of it to last the entire study. You don't want to have to switch materials halfway through.
All right, deep breath. You've done the work. You designed your study, you ran all the samples, you crunched the numbers. Now comes the big moment: making the call. How do you turn all that data into a final, definitive decision?
This is super important. Before you even run a single sample, you have to define what good enough looks like. You have to set the goalposts. We call this your acceptance criteria, or your allowable random error. And you don't just pull this number out of thin air. It's usually based on what the manufacturer claims their test can do, or it's part of your lab's overall quality budget.
And in the end, it really just boils down to this one simple comparison. You take the number you got, your observed standard deviation from your study, and you hold it up against the goal you set beforehand. The question is simple: is your result better than or equal to your goal?
And if your bar is shorter than the goal bar, well, it's that simple. You pass. Congratulations. You've successfully proven that the precision of your test in your lab meets the standards you set out to achieve.
And this is where we circle back to why those big, intense EP05 studies are so cool. Remember ANOVA? This is what it gives you: a beautiful breakdown of exactly where your imprecision comes from. Is most of the variation happening within each run? Maybe you need to look at your instrument. Is it mostly between days? Maybe it's an issue with reagent stability or different operators. This isn't just a pass-fail, it's a roadmap for continuous improvement.
All right, so let's boil this all down to the key takeaways. 1. Precision is all about consistency and random error. 2. SD tells you the absolute spread, while %CV gives you the relative spread. 3. Pick your study: the big EP05 or the faster EP15 based on your goal. And 4, a pass simply means your observed error is inside your allowable limit. That's the core of it.